Yeah, so I'm Alvin Noe Ladines, and in the next 30 minutes, I'm going to guide you in writing parsers for text-based file formats. So in a nutshell, our goal for today is to convert a text file, an output text file like this, into a NOMAD archive like this. So since this one is a prototypical output of a DFT code that contains like the parameters, the structure, and the steps in a geometry optimization. So since this one is an output of a simulation code, we are going to put the metadata that we parse from this output into under the run section. So the run section contains the method section, the program, the system, which contains the atomic structure, and then calculation, which contains the results of the calculation, like the energy and so on. So more specifically, the goals of this presentation is for you to be able to parse the metadata from an output text file, and then we look at how we write the parse results into the NOMAD archive, and eventually how do we interface our parser to NOMAD. So let's look at step number one, which is the actual parsing. So we provide a class called text parser, which you can find here, to enable the parsing of unstructured text files using regular expressions. So the thing that we need to provide is a list of quantities that are to be parsed. And each of this quantity, we provide a name of the quantity, the regular expression to match the output, the data type, shape, a function, string operation, which essentially operates on the parse string, and a unit. So, for example, we want to parse this part of the output, geometrization converge or not. So we define our text parser and provide a quantity called isConverge, and the regular expression is geometry optimization, and then we capture whatever comes from after this and before like a dot. So we see it here. And we provide a string operation, a lambda function, which says that if the parse string is equal to converge, then it's true. So, and then we essentially provide the path to our main file, in this case, like output.txt, for example. And then in order for us to get the actual parse value, we essentially use this .get function. Get, then the name of the quantity is converged. So just a quick note on the unit here. So we use the NOMAD unit standard, which you can find here. For example, the unit for energy, electric volts, is given by ureg.ev. Now, how do we, step two is writing the actual parse data into the archive. So we, of course, have to follow our schema. So we have to have our schema side by side with the parser. So this is our schema. As I've commented a while ago, we are parsing a simulation code. So we use the run section, so which is under entry archive. It's actually a repeating section, so expect multiple sections, multiple instances of this. So the run section is defined by this run class here, and inside it we have a quantity system which contains the system, and it's also a repeating section. And the system, inside it, we have the actual atomic configurations, which is defined by atoms, by class atoms. It's not a repeating, so it's not a repeating section. So we only have one atomic configuration per system. Yeah. So, and inside these atoms, we have the quantity labels, which is of type string and has shape given by n atoms. So to be able to write the metadata that we have parsed, we have to import, of course, our schema. We have to import archive and then our schemas here. And then we instantiate our entry archive like this. And then we we instantiate run, then we instantiate system. And we essentially just have to set atoms to be equal to an instance of atoms. And we give the labels as, for example, like this, HHO. And then we don't forget to essentially append the system that we have created here into run.system. And also we have to append the run that we have created here to archive.run. So those two are very important here. If you don't do this, the system and the run is not part of the archive. Yeah, so just a quick note on the schema. So a meta info section can be extended. So in order for us to do this, we define another class, called method, which is a subclass of the original simulation method that we have here. And then we just define this mdef is equal to section extends base section. So that means that all the quantities that we have here is also now part of this class here. And then we add the special quantity called myDFT special parameters, which is of type JSON. So we're expecting a dictionary here. Now, a very common source of error in writing data into the archive is that it does not match the schema. So you have to be very careful. So if you define your quantity to be dictionary like this, so you have to provide a dictionary. Yeah, so the third step is interfacing your parser to NOMAD. So our parser has a structure like this. So I structured my parser like this. So we have we have the my DFT parser under my parsers, and it has this init.py, this NOMAD plugin.yaml, which you have already seen in the previous talks. And we have this parser.py, the most important file that contains really the parsing. Of course, some test data and the test runner here, and some more auxiliary files. Now, it's very important to specify in NOMAD plugin.yaml this metadata. So we have to specify the plugin type. In this case, it's a parser. The category to which our code belongs, it's a DFT code, so we put it under atomistic code. We provide a code name, myDFT, and then we provide a unique name for our parser, which is parsers myDFT parser. And then we also have to provide the class name, which is essentially just the link to our parser, or the path to our parser. And then the Python package is this myparser.tft. Now, we also have to specify like this main file contents ref, which essentially matches, which is like a string that matches our main file or our output. So we have like this myDFT here, which essentially matches this one. Yeah, so you can provide some more stuff here, but I will not anymore talk about them. Like, for example, if your main file is like an HF5 file, you can specify also some quantities there that should be in your file. Yeah, in your nomad.yaml file, you have to essentially include these plugins. Then you put this include and these options. And under options, you specify the Python package, which is this. Yeah, so the next step is to essentially set up your parser. So how does your parser look like? You have your main file parser like this. So it's a text parser instance, and you have your quantities, like for example, version and other stuff, other quantities. And then your actual parser is this. You should provide this this function parse. Now this function parse should take in the path to the main file, the archive, and also the archive. So, and under this, you simply assign the main file that you have here in as a main file of your parser, and then you now create an instance of your schema, and then you assign values like this, and getting the data from your out parser. Like for example, the version here is out parser that get the name here is version. And again, don't forget to append the section that you have created here into the proper section, proper section, in this case archive. Yeah, so again, as a responsible developer, you have to test, of course, whatever you write. So you provide a test like this. So I put it under test my DFT. So you define a parser, an instance of your parser, and then you have things like you create generate an archive, an instance of the entry archive. And they essentially invoke this .parse, and then you put the path to the test main file, and then you provide this generated archive here. And then you assert stuff that you have parsed. For example, the program version should be equal to something. Yeah. So now to the live demo. Okay, so I'll show you now the actual code for parser. So here is parser.py under DFT. So of course the usual stuff, some import necessary libraries, and then you import here the text parser and also the quantity, the unit, and the schema. All of these are schema. And we have to import here because we sort of extended the method section to include some more quantities like special parameters. I don't know why there are two of these here, sorry. Yeah, and then we define the parser for our main file. So we have the quantities version, which is essentially this part here after this v, so it's 0.1. And then we provide, we parse the parameters, which is everything after parameters and before these two stars here. As you can see from the outputs, everything here. Yeah, this. And and then we provide a subparser for this string that we have parsed here. So we provide another instance of a text parser, and then we provide some more quantities. Like for example, the kgrades. Kgrade is like the three integers after kgrade, this one. And then the exe, the extension functional is this, the string after exefunc, and yeah. So you essentially know what these ones are. Now for the structure, so we have to parse everything after the structure and before these positions. So essentially this thing here. So you have to parse this. Yeah, and then we provide a subparser, which is again an instance of this text parser, and the quantities are the lattice constant, which is the float after the string alat here. So essentially this one, 10.47 here. And then the lattice constants, the lattice vector, sorry, which is like this three floats after this string lattice here. So we also parse is positions XYZ, which is like the string after positions read from. So this guy here. And then we parse now the geometry optimization section. So geom opt up to this geometry optimization. So essentially everything here. And then we parse the force tolerance, which is the float after force stall, like here, this guy here. And then we parse the steps in the optimization, which is like op step, and then ending at energy special. So essentially this guy here. Now it is, you have like, you have 3 steps here. So we have to specify here that our quantity actually repeats. So you specify repeats through here. So we expect multiple instances of this. And then finally is converge, again, is this guy here. Now, so we already have our main file parser. So we now define our parse function. So again, so we assign our parse function, the main file to our main file parser. And then we instantiate the run section, and then append the run section to archive. And then the program is given by instance of this program section. And then the name is mydft, and then the version is the version that it's the version that we parse. So we do out parser.get version. Then we populate the method section. So the method section are found here in outcar.parameters. And if there are none, then we create a method section, which we then append to section run. And then we go over all the items that we have parsed in parameters. And if it's kgrid, this guy here, kgrid, then we create the kmesh section and provide the grid as this one, parameters.kgrid. If it's a smearing, then we create an electronic section inside method, and then we assign the value for the smearing parameters, like for example, the kind and the width. And if a key starts with mydft, we essentially set it as an attribute of the method section. And next is the system section. So it's under structure. So if it's none, then we essentially read the structure using ASC. So we import asc.io.read, and we essentially provide the path to the file. And then this one means that we are expecting several frames. And then for each of these frames of ASC atoms, we create a system. And for each of and under systems, we create atoms. And then we provide now the values for the lattice vectors. So and we get it from this lattice quantity that we have here, that we parsed here. Yeah, and then if we have lattice vectors, we provide periodic is equal to true. And then the positions we have, we get it from the atom position. So get positions, if you know ASC, then this one's like the functionality to get the positions, and they are in angstroms. And then the labels, it's that get chemical symbols. And then finally, do not forget to assign the section atoms into system.atoms, and also don't forget to append the created section system into section run.system. Finally, the calculation section we populate. So we have we find it in this geometry opt, and then so we loop over all steps. So this one is a repeating section. So we expect several steps here, and each of these steps we create a calculation section, and then we append it to the section run.calculation. And to save the energy, to write the energy, we create an energy section under section calc. And then yeah, and then essentially set now the value for this energy by through this section here. Yeah, it will become clearer if you essentially look at now the metadata, which we don't have time to do now. And finally, we just a Another one is you can also provide, since this one is a geometry optimization run, we provide the workflow as a instance of this geometry optimization section. Okay, so that's essentially our parser. I've already set up my NOMAD and we try it. So I hope it works. So we create an upload here. Then we essentially take our output file and the XYZ file for our structure. So to load it, and we expect that it's a success. Okay, so you have now this. So it only parses, of course, the output.out main file. It doesn't parse the XYZ because that is only an auxiliary file. So if you open it, you essentially see this OBB page, which contains some metadata, the material which is constructed from the system section. So all of this stuff are provided by the normalization, this one, two, and these other guys. Then we see like a plot of the geometry optimization steps, the energy as a function of the steps in our geometry optimization, and some workflow graph here. Okay, so looking at now the data, it looks something like this. So we have our entry, and we expect our metadata to be residing here on the run. And then we look at the name of our program, IDFT here with the correct version. And then we have here our methods. So we also have like code specific ones, right? So if you click on this, then we also like see here like the code specific parameters that we have defined. And under system, you see like the 3 frames that corresponds to each of the steps in our geometry optimization here. So, and under each of one of them, we have these chemical compositions and the atomic structure, which contains labels, positions, status vectors. Yeah, cool. Calculation, we have a reference to our system essentially, and the values for the energy. So you have this total energy here and has this value, the XC energy has this value, and some special energy. Yeah, basically that's it. That's how you write parsers. So it's very, very simple. So for this prototype DFT code that we have to write a little more than 100 lines of code. So not bad. Yeah, so thank you.
Yeah, thank you very much, Alvin. Yeah, and as you see, it's super simple. I think the hard part for people getting into this is knowing about our metadata, right? I think it's having a file and get an idea how to parse it with a regular expression. Alvin explained it very well, and you can use the text file parser there to help you out as utilities. But then I think the tricky part is to know exactly how our schema looks like and what you need to instantiate. But I think NOMAD provides all the tools to learn about it, right? We have the meta info browser that you can use to see what the schema is. And also when you're used to NOMAD and have looked at enough examples or maybe analyzed a few entries or whatever, then you're also already pretty familiar with the structure of systems and calculations and what workflows are and so on and so forth. Yeah, anyhow, thank you very much, Alvin. And let's see if we have questions.